Hello, today I'm going to talk about boiling point elevation. There's a bit of math, so please pull out your calculator. I'll make this as simple as possible. So let's understand this. I'm going to read a little bit from the OpenStax textbook, okay? The boiling point of a liquid is the temperature at which its vapor pressure is equal to ambient atmospheric pressure. Since the vapor pressure of a solution is lowered due to the presence of non-volatile solutes, it stands to reason that the solution's boiling point will subsequently be increased. Compared to pure solvent, a solution therefore will require a higher temperature to achieve any given vapor pressure, including one equivalent to that of the surrounding atmosphere. Okay, so that is the reason, I guess pictorially here, worth 1,000 words, why solutions require higher temperature to get enough vapor pressure to form bubbles and have that appearance of boiling. Okay, so boiling point elevation, simple formula. Your textbook, the OpenStax chemistry textbook, leaves off the little I there, the Van't Hoff factor, and that's really bad. Okay, so this is a deviation from the textbook, but this is the most complete picture of the boiling point elevation. Delta TB stands for the boiling point elevation. It's how much higher of a boiling point, okay? Liquid water we know boils at 100, so it's going to be 101, 102, 103 degrees Celsius or something, okay? So the delta is going to be 1 or 2 or 3. All right, KB is the boiling point elevation constant. We'll see how it depends on the solvent. We're going to do water in the video, but in the lab we're going to do cyclohexane, which is something else. It's a different liquid. M is the molality of the non-volatile solute. So if you've got sugar water, it's the sugar, okay? So know what molality is. I is the Van't Hoff factor. Basically, it's the number of particles on the right side of a dissolution reaction. So it's going to be 1 for non-electrolytes like sugar or any kind of molecule, and it's going to be a number for ions. And we'll see how that looks like, all right? All right, so here's the table of solvents. This is table 11.2 from the OpenStax textbook. And so we're looking at the first column there. We have the boiling points of these different substances. Memorize, of course, water boils at 100. And we have KB, okay? So you're going to be given the KB or have to look up the KB for a particular solvent that you're working with. All right, here's our first example. What is the boiling point of a 3.2 molal sucrose solution? So step one, you want to find the KB for the solvent, okay? So this is an aqueous sucrose solution, which means there's water involved, so the KB is 0.512, all right? So that's table 11.2 in your textbook, all right? Next, what you want to do is determine the I. So sucrose, remember, is a non-electrolyte, so I is going to be 1, but if you don't remember that, you can find out what its formula is. Oh yeah, there's no metals in the formula, it's not ionic, it doesn't break apart to form ions. There's one molecule forming one molecule, so I is 1, all right? So the next what we do is we calculate the delta TB, all right, the change in boiling point. So it's 0.512 C over M times 3.2. The molalities here cancel. I'll just show you that the first time, and we're left with the units of degrees Celsius. Please do not write this as the boiling point for water. We're not going to take this jug of water and put it in the refrigerator back there to see if it boils. Remember that the last step is always to calculate the boiling point of the substance. Now the normal BP or boiling point of water is 100, so we add that to the 1.6 to give us a final boiling point of 101.6 degrees Celsius. This is a very small increase, but it's measurable, and we have these formulas to describe it. Example number 2, what is the boiling point of 1.8 molal aqueous potassium permanganate? All right, so remain calm. So first step, you want to find the KB for the solvent. This is aqueous, so that means water. It's 0.512 degrees C per molality, okay? Next, we want to determine what I is. So a little bit of head scratching here. What is potassium permanganate? You can look it up on chemspider.org, Wikipedia, or something like that, and you find out that its formula is KMNO4. Now, permanganate is a polyatomic ion that all stays together, remember, when it dissolves in water, And so if you count the particles, we have a total of 2 on the right-hand side. I've highlighted them in orange. We've got 1 potassium ion and 1 potassium permanganate ion in this balanced chemical reaction, right? And so I is 2. When you have different ionic formulas, you've got to add up all the different coefficients. So if it's 2 here and 3 here, it's going to be a total of 5. Next, we want to calculate the change in the boiling point. So it's Kb times m times I. So there it is. And notice how there's a 2 there in the formula. And when you multiply that all out on your handy-dandy calculator, I get 1.8 degrees Celsius. Now again, that's not the boiling point of water. Boiling point of water is very high. Please do the last step. Always add this to 100 degrees Celsius to get a final value of 101.8 degrees Celsius. Feel free to watch this video again, but if you do need other different varieties of problems, check out my channel for more worked problems on boiling point elevation. Thanks for watching. Please like, please subscribe. I hope this helps you with the formula.